which was an abelian group under addition. With identity element 0, with inverse, if we write the inverse of A is denoted minus A in the ring notation because A plus minus A is 0. It also has a multiplication, which I'll write A times B, or the book sometimes writes A cross B. And the multiplication is associative. So A times B times C is A times B times C, associative. And it's distributive. A times B plus C is A times B plus A times C. And if the ring is not commutative, you have to do this in the other way. B plus C times A is B times C plus B times A plus C times A. And if A times B is equal to B times A in the ring, you say it's a commutative ring. And from the rest of this term, all we're going to do is commutative rings. So I'm going to leave this, just put this as an axiom for a ring. Although you should be aware that it's very interesting in math to study non-commutative rings, like matrix rings are non-commutative rings. But we're going to study the theory of commutative rings. And when you have an object in math that you've defined like a group or a vector space or a ring, you want to know what a homomorphism is. So we talked last time about what a ring homomorphism is. So F from one ring to another. And it's a map of sets, which is a group homomorphism. So in particular, it takes 0 to 0 prime. It satisfies F of A times B is equal to F of A times F of B. So it commutes with the multiplication. This is the multiplication in R. This is the multiplication in R prime. And it takes 1 to 1 prime. I should have said that the multiplication has an identity. I'm sorry. 1, which has the property that 1 times A is A times 1 is A for all elements in the ring. So it preserves the ring structure. It takes the ring structure on R to the ring structure on R prime. And we saw that if we had a homomorphism and we defined I as the subset, the kernel of F, which is the set of A and R, such that F of A was the 0 element in R prime, that was a subgroup because it's the kernel of a group homomorphism. So it's a normal subgroup, but that's obvious that it's normal because it's an abelian group. And it has the unusual property that it's stable under multiplication by any R in R. So if you have A in I and you have R in R, then RA is in I. So it's not just closed under multiplication, but it is stable under multiplication by any element in the ring. And that's because if you apply F to RA, you get F of R times F of A, which is F of R times 0 prime, 0 R prime, because A was in the kernel. And anything times 0 we saw was 0. And so this element is also in the kernel. So it's stronger than you might think of a sub-object. And we call subsets of R that are subgroups stable under multiplication ideals. Such subsets are called ideals, I in R. And the study of ring theory is really the study of the property of ideals, as we're going to see. It's a surprising thing that normal subgroups play an important role in groups, but then there are very interesting groups that don't have normal subgroups. But interesting rings have a lot of ideals, and we're going to see it. We're going to study them. And I noted last time that to each ideal, there is a canonical ring homomorphism F with kernel equal to I. So the ideals, these subsets closed under multiplication from the ring, are exactly the kernels of ring homomorphisms. And you do that by letting R prime be the set of cosets of I. After all, it's a subgroup, so it's the quotient group, quotient abelian group. That makes sense. And to turn this into a ring, and we have a map from R to R prime, which is a group homomorphism from our theory of abelian groups, which takes an element in R to its coset modulo this ideal. And I've written that additively because this group law in R is an abelian additive group. So we have a surjective homomorphism of abelian groups with kernel I by our theory of groups. And to show that this is a ring homomorphism and that this is a ring, I have to tell you how to multiply two cosets. And then to check that that multiplication is preserved by F. Well, the definition of multiplication is that if you want to multiply the coset R plus I times the coset S plus I, then it's by definition the coset RS plus I. And to check that this actually makes sense, namely that if you changed your coset representative here and your coset representative here, you would still be an element of this coset, the multiplication. You just have to check that if you multiply anything in this coset, R plus I, times anything in this coset, S plus J, where I is in I and J is in I, then I claim that the product lies in this coset. For anything in this coset times anything in this coset, there's a unique coset that contains the product, and that's this. And the reason is, and this uses the fact that I is an ideal, not just something stable under multiplication. If you use the distributive law on this a couple of times, you find that this is RS plus IS plus RJ plus IJ. Okay? Now I claim that all these elements are in I, so that this product is in this coset. And the reason is, here's an element of the ideal times an element of the ring. Here's an element of the ideal times an element of the ring. And here's the product of two elements in the ideal. So by using the property of the ideal, we see that the product of anything in here times anything in here is in this coset. Consequently, the multiplication is well defined. And then you have to check that it satisfies the ring properties. But it's clear that this is true, because if I take f of R times S, that is the coset f of R, which is R plus I, times the coset f of S, which is S plus I. So I've constructed the ring structure on R prime so that this map is a homomorphism of rings. Okay? So last time we got the basic notion of what is a ring, what's a ring homomorphism, what's an ideal. Okay. Now, we saw that the ideals always contain the following. There are always two natural ideals in a ring, just like there are always two subgroups of a group. Two obvious ideals in R. I, the zero ideal, just consisting of an I equals R. Here, the quotient ring R prime, which is R mod I, is just R. And the homomorphism is the identity. So that the only element mapping to 0 is 0. And here, R prime is the zero ring. And the map F of any element in R is just 0 in R prime. That's a ring homomorphism. Note that in the zero ring, 1 is equal to 0. So this does take 1 to 1. Okay, so any ring has these two ideals. Note, if R is the zero ring, these are the same ideal. If R is not equal to the zero ring, these two ideals are distinct. Because we saw that if you are not equal to the zero ring, 0 is not equal to 1 in R. This ideal doesn't contain 1, and this ideal does contain 1 because it contains everything in R. Okay? Now, is it possible for a ring to only have two ideals? So we've seen it's possible for a ring to have only one. So the only ring that has one ideal is the zero ring, because otherwise I have two distinct ideals. So here's a little proposition. If R has only one ideal, R is the zero ring. We've already proved that. If R has only two ideals, then R is a field. In fact, if and only if R has only two ideals, if and only if R is a field. And of course, those two ideals are R and the zero ideal. So that's an interesting characterization of fields. Remember, a field is a ring where every non-zero element has an inverse. A ring where every non-zero A has an inverse, a multiplicative inverse, A inverse in R, with the property that A times A inverse is the identity element in R. That's really the definition of a field if you look at it. A field is, you insist a little bit more than a ring. You have to have an addition, you have to have a multiplication, and any non-zero element has an inverse. If you look back at our theory of vector spaces over an arbitrary field, we needed this inverse in a lot of places. For example, when we proved that every vector space had a basis. Things like that. Okay, let's prove this proposition. The first part has already been proved. So now we're going to go both directions. So let's assume that we are in a field. Let's assume R is a field, and that I is a non-zero ideal. If I'm going to prove this direction, which I'm going to start off by proving this direction, I then have to prove that the ideal is the entire ring. Right? I mean, I always have, if I have a non-zero ring, two ideals. So I've assumed I'm in a field. I've assumed that I know I have these two ideals. So I start with a non-zero ideal, and I want to show that I is the entire ring. All right? Well, take some element A in I with A not equal to 0. If it's a non-zero ideal, it means it contains some element which is non-zero. All right? Then A has an inverse. Since A has an inverse, call it R, which is A inverse in the ring, 1, which is A times R, is in the ideal. Right? A is in the ideal. Whatever the inverse is, it's in the ring. So anything in the ring times the ideal is in the ideal. So 1, which is the product of A and A inverse, is in the ideal. Since 1 is in the ideal, for any R in R, R times 1, which is R, is in the ideal. Here's an element of the ring. Here's an element of the ideal. Okay? So that just proves that any element is in the ideal. So hence, I is equal to R. So if you're in a field and you have any non-zero element in an ideal, then multiplying it by its inverse shows 1 is in the ideal. Then multiplying by any element shows that the ideal is the entire ring. That shows, by the way, that another way of describing these two ideals, this would be the ideal 0, the principal ideal generated by 0. This would be the principal ideal generated by 1. All multiples of 0 are just 0. All multiples of 1 are just the elements of the ring. Right, so the last time we had a notation for an ideal, if I consists of all multiples of A, we say it's a principal ideal generated by A. So these two natural ideals are both principal ideals. This is the principal ideal generated by 0. This is the principal ideal generated by 1.
What if you have a field with an element like 2 to the 1/3 in it? Then how would you, maybe I should say ring. You have a ring with an element like 2 to the 1/3. How do you generate all the elements just by adding 1? Maybe I'm missing something.
No, it's not by adding 1. It's all multiples of 1. And anything is a multiple of 1. Right? Because anything times 1 is itself in a ring. So once you have 1 in the ideal, you have everything in the ideal, and the ideal can just be described as multiples of 1. Kind of stupid ideals. All right, so that shows that if I have a field, I have only 2 ideals. Now let's prove the opposite direction, that if I have only 2 ideals, my thing is a field. All right? So let A be an R, and consider and assume A is not equal to 0, and consider the principal ideal generated by A. All multiples of A. That's an ideal because this is closed under addition and multiplication from the ring. If I have only 2 ideals, this is not the 0 ideal, so it has to be the entire ring. Now, one element to this ring is 1. Right? So I have to be able to write 1 as some multiple of A. Well, that's the inverse. That is the multiplicative inverse of A. So if I have only 2 ideals, I've just proved that any non-zero element has a multiplicative inverse, which means I'm a field. Okay? So fields are distinguished among the commutative rings by having a very small supply of ideals. Let's take a look at a very simple ring that isn't a field and see where the other ideals are. Let's take the ring R, which is Z mod 4. Z. Integers mod 4. That's not a field because 4 is not a prime number. Okay? So what are my ideals here? Well, you have the ideal generated by 0. You have the ideal generated by 1. Those are my 2 famous ideals. And then, if you want to think about it, if I want to make a non-zero ideal that isn't the ring, I better choose, and I want it to be a principal ideal, I better choose a generator which doesn't have an inverse, a multiplicative inverse. Can you see an element in this ring, Z mod 4, which has 4 elements in it, by the way, 0, 1, 2, 3. You add them and multiply the mod 4. Is there an element that doesn't have a multiplicative inverse? 2. So I could take the ideal generated by 2. This is the ideal R, and this is the ideal that consists of the elements 0 and 2. And if you check, that's closed under addition mod 4, and it's closed under multiplication by anything mod 4. Because if I multiply by anything mod 4, times 0, it's 0, and times 2, it's even. Right? So it's still in this set. So here's the third missing ideal. Okay? If I take R equals Z mod NZ, that has an ideal generated by D for all D dividing N. They may be slightly different. They may be the same ideal. I mean, for example, if you take the ideal generated by 1, it's the same as the ideal generated by minus 1, which is also a divisor of n. But you get more and more ideals the more factorizable n is. So in particular, if I took r equals z mod p to the kz, then the distinct ideals are 1, p, p squared, p cubed, all the way up to p to the k, which is the ideal 0. So you have a decreasing chain of ideals here that looks like this. This is the entire ring that contains the multiples of p, which contain the multiples of p squared, which contain the multiples of p cubed, all the way down to the multiples of p to the k, which is just the 0 ring. So that's a descending chain of ideals. Just like here, we have the descending chain of ideals 1, 2, 0. So you have that any time you have prime power. This is a little bit more complicated because you have descending chains of ideals depending whether d divides d prime. And in general, the set of ideals forms what's called a lattice. You know, some ideals contain some others, etc. And that's a very interesting thing to study. And the only really simple case is this case. Now, these rings have only a finite number of ideals. And the reason they have only a finite number of ideals is they have only a finite number of elements. So there are only a finite number of subsets. And ideals are in particular subsets. So you can't have more than a finite number of ideals. However, if you want to get to a ring that has an infinite number of ideals, where things start to get interesting, you can go to the basic ring of them all, the integers. Z has an infinite number of ideals, distinct ideals. And every ideal, in fact, is of the form n, all multiples of an integer nz, for n greater than or equal to 0. And the reason is that every subgroup is of that form. We proved that a long time ago. And in particular, it's a subgroup, and then you check that this is stable under multiplication from the ring, as these are the full list of subgroups, and all are stable under multiplication from z. And they're distinct because I've assumed the generator is greater than or equal to 0, and you find that I sub n contains I sub n prime. Maybe we should call this I sub n, generated by this positive n, provided, if and only if, n divides n prime. Because a particular element in this ideal is n prime, and that'll be contained in I sub n if n prime is a multiple of n. So the lattice of ideals here is the same as the lattice of all positive integers ordered by divisibility. And they're an infinite number of positive integers, so they're an infinite number of ideals. Notice that you get the 0 ideal when n is equal to 0. You get the full ring when n is equal to 1. Otherwise, you get proper subrings. The quotient R mod I sub n, in this case, is just z mod nz. It's this finite ring. Okay. Now, it's very rare that when you get a ring, you can write down all its ideals. Very rare that you get a case like this where you can write down all the ideals. But I'll give you one more ring for which we know all the ideals, where you can make a list of ideals. They're an infinite, usually, well, they're always an infinite number in these rings, but so another important ring where we know all ideals is the following ring. Let F be a field. Well, we know the ideals there. They're kind of stupid. But we take a slightly more complicated ring where we take the ring of polynomials in one variable over the field. So this is all things of the form an x to the n plus a1x plus a0, where the coefficients ai are in our field, and where you add and multiply polynomials just like you add and multiply polynomials. Okay? Now, we call a polynomial in this monic. We say, let's call this polynomial p of x. We say p of x is monic if the leading term here, if an is equal to 1. So that it starts off with first coefficient 1. And in general, if you have any polynomial, you can multiply it by a scalar in the field so that it becomes monic. If q of x is any polynomial, there exists a unique value c in the field such that c times q of x is monic. Well, in f star, yeah.
So n's not fixed, right?
No, n could be arbitrary. I should have said n greater than or equal to 0. Polynomials of arbitrary degree. Otherwise, it's not closed under multiplication. So if you just took polynomials of a fixed degree and you multiplied them, you'd overflow. So when I write it like this, when I write a polynomial like this, the implicit assumption is that this highest coefficient is not equal to 0. Because if it were equal to 0, I wouldn't write it. Right? And if an is not equal to 0, we see the degree of this is equal to n. That's a definition of a number associated to any polynomial. The constants have degree 0. The linear polynomials have degree 1. So I claim that if I take any polynomial of degree n, there is a unique constant in the field such that when I multiply the polynomial by that constant, it's monic of degree n. And the proof is, take c equal a sub n inverse. And since I'm in a field, every non-zero element has a multiplicative inverse. If I multiply this polynomial through by a sub n inverse, I change this first coefficient to 1. If I multiply through by anything else, I don't get 1. So there's a unique way of making a polynomial monic by scaling it. Okay? I'll make a remark after I put up the theorem. Here's a proposition about ideals in the polynomial ring over a field. A very important theorem. Proposition. Every ideal I in the ring R equals f of x is principal generated so I is a principal ideal generated by the monic polynomial f in I of least degree. And in particular, another thing is that every monic polynomial generates a unique ideal. So the ideals as a set are in one-to-one correspondence with monic polynomials. And the ideal associated to f contains the ideal associated to the monic polynomial g if and only if f divides the polynomial g. Namely, that g of x is f of x times another polynomial q of x. So it's very similar to the situation with the integers. And notice that making a polynomial monic by scaling is exactly... See, I could have taken this as the same ideal as generated by minus n. They're the same ideal. The multiples of n are the same as multiples of minus n. So the monic condition is like this condition. I've been able to choose a unique generator by multiplying it by certain elements, which are in fact the units in the ring. I should have said that. This is the unit group. That happens to be the unit group. which I'll also show you that, of R. Okay, let's at least prove that every ideal is principal generated by the monic polynomial in it of least degree. That gives us a description of all the ideals, just the monic polynomials. Okay, so this is the same proof as we used for the integers. We're going to do an analogy of the Euclidean algorithm. Analog of the Euclidean algorithm for polynomials over a field. If f and g are two polynomials with the degree of f greater than or equal to the degree of g, the degree makes sense, it's the size of the highest term, then f is equal to g, let me write it, f of x is g of x times q of x plus r of x, where this is a polynomial and this is a remainder polynomial. This is the quotient polynomial, this is the remainder polynomial, and r of x has degree less than, the degree of r is strictly less than the degree of g that you're dividing by. So you can't always divide one polynomial into another evenly, but you can do it by leaving a remainder which is of degree less than the degree of the thing you're dividing by. So this is just a process of constructing q of x by successive solution of linear equations. So let's just try this so that we understand what the heck is going on over the complex numbers. Suppose I started with f of x as something like x cubed plus 2x squared plus 3x plus 7. And suppose g of x, where x squared plus x plus 1, just to give an example, I have to show that I can write this polynomial as a multiple of this plus something of degree less than this. All right, the first thing I have to do is get rid of the x cubed term, which I would do by multiplying this by x. So x times g of x is equal to x cubed plus x squared plus x. I take the difference between f of x and x times g of x. I'd be left with the polynomial 2x squared minus x squared, so that would just be x squared. Then I'd have 3x minus x, which would be plus 2x plus 7. That still doesn't have small enough degree. I have to subtract some other multiple of g of x to get the degree down. Well, I would multiply g of x by 1 to cancel the x squared term. At each case, you just have a simple equation to solve to cancel the next term. So I'd find that f of x minus x times g of x minus g of x would cancel the x squared term, and it would leave me with x plus 6. And that would be this equation. Namely, q of x in this case would be x plus 1. That's the multiple of g of x that I have here. Well, it would be, yeah. And r of x would have degree less than g of x, would be x plus 6. And you just do the exact same thing for two general polynomials. You find the highest coefficient of q by finding what you have to multiply g of x to cancel the highest coefficient of f. Then you find the next coefficient of q. And you keep working your way down until you've eliminated all the coefficients of f that have degree up to the degree of g. And then what you're left with is something that has degree less than the degree of g. And you'll see you needed to be a field at various points, because here I had coefficients here. But if g of x had this coefficient, for example, 2x squared, like this, then the first thing I would have had to do was take the inverse of 2 and multiply it like that. So in this Euclidean algorithm process, you frequently have to invert coefficients. In general, you can do it if the first coefficient of g is a unit, but you have this expression. So it's just normal polynomial division. Convince yourself that this works. It's not a deep fact. All right? Now, let's prove that any ideal is generated by the monic polynomial in it of least degree. So let I be an ideal, and choose a polynomial if it's not 0. Okay, if I is not equal to 0, take f in I of minimal degree. There has to be something in I of minimal degree. If it's non-zero, there might be several things of degree 7, but choose one of them. All right? Scale it. Scale f by, let's say the minimal degree is n, by c, which is an inverse, to make f monic. It's still in the same ideal because c times f is also an element in the ideal. C is an element in the ring. So I now have a monic polynomial of minimal degree in I. All right? Now, I've got this organized a little wrong. Let h be another polynomial in I. And write h as a multiple of f, I'm doing it backwards here, but never mind, plus a remainder term where r of x has degree less than the degree of f, which is n. Okay? F of x is in I. Therefore, this multiple is in I because it's stable under multiplication from the ring. Therefore, h of x minus q of x times f of x is in I. Because here's an element in I, here's an element in I, and I is a subgroup. Therefore, r of x is in I. Right? But r of x is the non-zero, but f is the element in I which is non-zero of the smallest minimal degree. Therefore, the only possibility is that since r of x is in I, these two things imply that r of x is equal to 0. It's the only thing that's possible. Because if it was non-zero and it has degree less than the degree of f, it would have been our better choice than f. Therefore, anything in I, because r of x is 0, is a multiple of f. Therefore, the ideal itself consists of all multiples of f by the minimal polynomial of least degree. Yeah?
What makes something a principal ideal again? As opposed to
All multiples of a single element. I'm going to give you a non-principal ideal too. So it means that anything in the ideal is the multiple by an element in R of a fixed element in that ideal. It has to be one element. So here, in the integers, we chose the smallest positive integer in the ideal. That did it. In the polynomials, we take in some sense, the smallest monic polynomial in the ideal. Okay? Okay. Now, this has some nice properties because if we've got a list of ideals and we're able to construct a ring homomorphism, then one of these ideals has to be its kernel. Right? So let me give you an example of a ring homomorphism, and let's see if we can figure out its kernel. Consider the map from R, which is f of x, to f that takes a polynomial, f of x, and it takes it to its value at a point C, where C is an element in f. And namely, you just take your polynomial. Where is thy poor polynomial? I've erased my poor polynomial. I take my polynomial f of x, which is an x to the n plus a1x plus a0. I think of it as a function on f by f of c is an times c to the n plus a1 times c plus a0. That's an element now in the field, because this is an element in the field, and this product is in the field, and this power is in the field. So you just add them all up, you get an element in the field. I claim that this is a ring homomorphism. Well, you have to check. Let's call this map, because I can't use the word f, because f is my polynomial. Let's call this map H. It's a homomorphism. So you have to check that h of f plus g is h of f plus h of g. And you have to check that h of f times g is h of f times h of g. And you have to check things on the identity element and things like that. Well, if you evaluate the polynomial f of x plus g of x on C, you get the value of f on C plus the value of g on C. You're just adding these coefficients. So, right? And that's this. And if you evaluate the polynomial f times g on C, well, again, you're just multiplying two functions and then evaluating them on C. So you get the value of one function on C times the value of the other function on C. So this map that takes a polynomial to its value at a fixed element in the field is a ring homomorphism. Its kernel has to be one of our friends up here. There has to be some monic polynomial that generates the kernel of this. Well, we better find something that's in the kernel of this. An element in the kernel would be a polynomial where when you evaluate it at C, you got 0. No constant has that property except 0, because if you evaluate any constant at C, you just get the constant. So we don't have any polynomials of degree 1, degree 0 in this ideal. Is there a polynomial of degree 1, a linear polynomial that vanishes at C? X minus C. And that has to be, that's a monic polynomial. The polynomial f of x, which is x minus c, is monic of degree 1 with f of c equal to 0. So, any f in I is a multiple of x minus c. Got it? So far, so good? Because it has to be generated by the monic polynomial of least degree. There are no monic polynomials of degree 0 that vanish at C. Unless, yeah, that's right. So here it is. So in other words, corollary, if f of c is equal to 0, then f of x is equal to x minus c times g of x. Corollary, a polynomial of degree n has at most n roots over a field. Remember we used that in our theory of characteristic polynomials? Why? Every time I have a root, I get a divisibility. I'm left with a polynomial of degree n. This has degree n. This would have degree n minus 1. By induction, this has at most n minus 1 roots. Therefore, f has at most n roots. So that's our proof that over any field, a polynomial has at most n roots. Very important fact. This was discovered by Euler and is probably the beginning of modern algebra. It's not true over a ring, as we saw. If you study polynomials over the ring Z mod 8, and you study the polynomial x squared minus 1, it has 4 roots. So that's polynomial of degree 2 that has 4 roots. But over a field, polynomials of degree n have at most n roots, and it's by this principal ideal property. Okay. Now, someone asked me about, well, maybe every ideal is principal. Can we come up with a ring where not every ideal is principal? So I'll just give you an example now without, wave my hands at it right now without proving it. Consider the example of a non-principal ideal. Take the ring R, which is polynomials over a field, but in 2 variables. So these things are all the things of the form summation of a, ij, x to the I, y to the j, I is equal to 1 to n, j is equal to 1 to m, where the aij are elements in the field. So such a polynomial would look like a00 plus a10x plus a01y plus a11xy plus a20x squared plus etc. And you multiply just like you multiply polynomials in two variables, and you add by components. And of course, the degrees in any given case are bounded, but can be arbitrary in general because you have to multiply them. And consider now the map. We'll call it H again, from R to the field, which takes an f of xy and evaluates it. I don't care. Let's evaluate it at some points. Let's take it to f of 0, 0. So it just means you take x equals 0 and y equals 0. All these terms go away, and it's just the value a 0, 0. Okay? I claim that's a ring homomorphism. Same reason that evaluation of polynomial one variable is a ring homomorphism. You add two polynomials, you add their values at 0. I mean, if you add them, you're just adding these constant terms. If you multiply two polynomials, it's a complicated operation, but the one thing that's simple is you multiply their constant terms. Okay. So that's a ring homomorphism. What's its kernel? Is not generated by one element. So it's not principal. Why? Well, are there any constants in I? No, just 0. But can you give me some simple polynomials that are in I? Yeah, it certainly contains the element x. It certainly contains the element y. I mean, the polynomial x goes to 0. The polynomial y goes to 0. Any multiple of the polynomial x goes to 0. Any multiple of the polynomial y goes to 0. And if you think of all these polynomials, they're just the collective multiples of x and y. Any such polynomial can be written as some multiple of x plus some multiple of y, not in a unique way. So in particular, the ideal I is certainly the ideal generated by x and y, which consists of all multiples of x plus all multiples of y. But it can't be generated by a single element. So you just have to sort of wave your hands at that. I mean, how could it be generated by a single element? Then x would have to be a multiple of that element, but also y would have to be a multiple of that element. And the only thing that x and y are both a multiple is of constants. And there are no constants in the ideal except 0. So that's the reason. If you ask for an ideal, here it is. It's a kernel of a homomorphism, but it can't be generated by one element. It's not the multiples of a single element. So this is, in some sense, a more complicated ring than the polynomials in one variable because we're going to have trouble describing its ideals. You can't just say, well, you just take all polynomials of this form and take their multiples. Okay. I just want to end with one cute remark. I said that Z, the integers, is the basic ring. It is. It's as basic to ring theory as the identity element is to group theory. So for any group, have a subgroup which is just the identity element. Namely, there's a homomorphism from E into your group that takes E to E. That's kind of stupid, but that's the only natural subgroup we know of a group. You can't do that. You can't do anything more for a group than just put the identity element in because the group just has the identity. But a ring has more. Any ring, commutative, of always R, there is a natural